Hey guys, welcome back to my channel. Um, Today I was gonna go into heaps or whatever the next chapter is, but then I thought maybe it's better if we solidify um, the binary search tree that we went through yesterday with another example. So I try to solve a question of medium difficulty, and it was honestly not that difficult. I'll share the screen with you guys. Yeah, so basically you're given a root node like always and value this time to insert into the tree, and we have to return the root node of the BST after the insertion. It is guaranteed that a new value does not exist in the original BST. Um, so basically you're adding the value that's given into a leaf node, right? So that in this case is a children node of 7. In this case, that would be a children node of um, 5, 2, 3, 4. No, wait. No, this was for first one. Yeah. So that would be the last element, right? Um, yeah, yeah, exactly. So we can always insert a new node, the value given, as a children node of a leaf, right? So in this case, 25, I guess, it's a children node of 70. Here, it's a children node of 3 as well. So that's why it goes right after 3. For example, 3. So to define what leaf that we want to use, so on the last node, uh, when we go through this with the DFS, uh, it could be either left node or right node, right? So we can use here the BST logic, which is if it's smaller, if the value of the node is smaller than the value, then we insert into the right subtree. And if the value is lesser than the value of the node, then we insert it in the left subtree. So yeah, so as you can see here in the tree diagram, you can already see that the 7 is bigger than 4, so it is inserted into right subtree, whereas 2 is smaller than 4, so it is inserted to left subtree. Children node as well, 3 is bigger than 2, so it is inserted into right subtree. So yeah, it's all BST, BST. Um, and it just goes on and so forth. So now, like yesterday, what we did with the question BST, I think that was also an insertion. We can also use a recursion, like treating the whole recursion process as a black box. So we just give a function that the function that we are gonna move the use of recursion on is going to keep on repeating itself, uh, and then somehow we get our answer. So although we don't know how it works, well, we can kind of explain how it works, but it's hard to explain. We know that it's very simple because um, if the root is null, then we return the tree node, the value of the tree node, so nothing happens. So that's a base case. And if the value, like I previously said, following the BST logic, if the value is bigger than the value of the node, then we insert into the right subtree, And if the value is lesser than the value of the root, so if the children's value is lesser than its root value, then we insert it into a left subtree. So and after that, in the at the last, we insert the root. We return the root. I mean, so we can just go dive into the code, I guess. So we just write down the base case first. So if not root, then return. In this case, it's tree node val. Now, if the value of the children is bigger than the root node, then we have to insert it into the right subtree, right? So that will be if val is bigger than root dot val, then root dot right equals to, what would it be? Root dot right is equal to the self root dot right, yeah, self right, no, self insert. So because we have to use, we're using recursion here into VST, and then root dot right, and then value, right? Root dot right and value. Yeah. Now, if, or can we use else? Yeah, we can also use else. And because that just signifies that when the value is lesser than root val, root dot left equals the same logic, right? So self-insert into PST root left of val. And then later, when the recursive approach is done, we return the root. And let's see if this works. Oh, it works. Damn, that was pretty easy, right? So, like we always do for BST, although iterative approach also works, we just simply use the DFS and the on top of that binary search tree approach. So if the right subtree is bigger than the its root, then um, we define the right side of the root as the self insert into BST root dot right val, and that's how we recursively apply this function on the right side, whereas if the condition is else, then we recursively apply this function on the left side. And at the end, we get the output as we want. All right, that was pretty simple, guys. But I guess most of the recursive questions are going to be like this, the DFS binary search trees also. I guess that was it for today, guys. I'm pretty tired. Um, hopefully tomorrow we're going to move on to the next chapter. I'm going to move on to the next chapter for sure. And yeah, I'm excited. Let's see how it goes. Thank you guys all for watching, and see you guys tomorrow.